Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall study functions of a complex variable. In our first chapter, we have studied complex numbers, definition of complex number, representation of complex number in complex plane, polar form of complex number, and we have seen how to sketch regions in a complex plane in our first chapter. You may please refer these lectures that we have studied earlier. Now, as a second chapter, we shall consider analytic functions. In this chapter, we are going to study functions, mappings, transformations. Then we shall define limits of functions, differentiation of functions, continuity, etc. And in that, the first lecture is functions of a complex variable. I have written the definition. We shall see the meaning of it. Let S be a set of complex numbers. A function f denoted by f defined on S is a rule that assigns to each z in S a complex number w. So, it is a rule that assigns every z in S a complex number w. That means, if you consider this as S and S is called the domain of definition of the function, and suppose there is another set of complex numbers, both are sets of complex number t, and f is a function from S to t such that it assigns every z in S a complex number w. These are related by the rule f. So, or we have the f of, this is denoted as f of z is equal to w, and the number w is called value of function f, value of function f at z, and it is written as f of z is equal to w, or w is equal to f of z. See, this w is called image. See, when the w is called image of, or the image of z, and z is called the inverse image. Inverse image of w. So, this is image, w is image, and while z is inverse image of w. And you see, S is, the set S is called the domain of definition of f. So, this is the domain of definition of the function f, and all those points in S are mapped or related by the rule to exactly one point, that is w. So, this is a mapping, and the image of entire set S, entire set S, which is domain of definition of f, is called the range of f. Range of the function f. And now, for example, we shall consider z is equal to x, complex number. Z is a complex number, w is also a complex number, and the complex number z we shall denote by usual way, that is x plus I y. Let z is equal to x plus I y, and this complex number, and w is u plus I v. Then f of z is equal to w, f image of z is w. The definition of function is the same as that we have studied in calculus. That means it is a relation between two sets such that every element in the domain is mapped to unique element in the codomain, and this set, the set of all images of points in S is called a range of S, a range of F. So then f of z is equal to w, therefore f of z is x plus iv, x plus iy, and that is w is u plus iv. Again, this u and v are functions of x and y. So therefore u is real part, v is imaginary part, and it can be written as u is function of x and y plus v is also function of x and y. So thus this f of z is written as f of z is equal to w is written in this form. And now we may consider an example like this. Example as let f of z is equal to z square, or w is equal to z square. Then we have this w is equal to z square, but what is z? Z is x plus iy whole square. Z is a complex number written in usual form as x plus iy, and its square is now can be expanded as x square plus 2ixy plus I square y square, but I square is minus 1, and therefore we can write this as x square minus y square, and this will be real part, and plus if you take I common, then in bracket it will remain 2x into y, and thus this is u function x, u of x comma y plus I, and this is v of x and y, and thus u is, so this is w, thus u is x square minus y square, real part of the function f of z. And therefore u is x square minus y square and v is 2xy. This is v and u. So for the function w is equal to z square. Now in polar form we can consider the same function. In polar form, see we have z is equal to r e power I theta, and therefore the same function w is equal to z square. Then so w is equal to z square, this becomes square of this r e power I theta whole square, or that will be r square e power I into 2 theta, and this we know by Euler formula, e power I into 2 theta is cos 2 theta plus I sin 2 theta, and further this is equal to r square cos 2 theta plus I into r square sin 2 theta. And now we write this as again u plus iv, and where here u is function of r and theta. In polar form, this is u r comma theta plus I v r comma theta. So this is the expression in polar form, where u is function of r and theta, and that is r square cos 2 theta, and v is function of r and theta, which is r square sin 2 theta. So in this way we can express a function in the form and its image in the form of u plus iv, where u and v are functions of complex variable. Now we shall consider a polynomial function. Polynomial and rational function. And for polynomial function, let n be a non-negative integer. And further, let a0, a1, etc. we shall denote as complex constants. a0, a1 and so on up to an be complex constants, that means complex numbers, where an is not equal to 0. Then a function p of z denoted by p, it may be denoted by any notation. Here it is denoted by p of z and expressed as a0 plus a1z plus a2 z square and plus so on up to an z power n is a polynomial of degree n, is a polynomial function, is called polynomial function of degree n, because an is not 0 and here n power of integer power of z is n, highest integer power of z is n. So therefore it is a polynomial function of degree n. And likewise the rational function we shall define as quotient of two polynomials. The quotient of polynomials, or you may just consider as quotient of polynomials, p of z divided by q of z, where q of z is not equal to 0, is called rational function. Here we should note the domain of definition is the entire z plane. The domain of definition of f of p of z is the entire z plane. That means z is any complex number. And here the domain of definition is all those numbers for which q of z is not 0, because it is at the denominator and denominator must not be 0. So these are called polynomial function p of z expressed in this form, and this quotient form is a rational function. Now we shall have some examples of functions and express it in real and imaginary part. I have written here two problems. We shall solve these problems one by one. Here first problem is, for each of the following functions below, describe the domain of definition of f. So domain of definition is important, where the function is defined. And here the first function is given as f of z is equal to 1 upon z square plus 1. So for solution A, Now see, this function is defined for all values of z except the denominator is not 0, except the denominator is 0. That means the denominator must not be 0. F of z is equal to 1 over z square plus 1 is defined for all z, complex numbers z, all z except for which z square plus 1 is equal to 0. That is, z square is equal to minus 1, which is I square, and that is z is plus or minus I, and that means the function is defined for all values of z except z is equal to plus or minus I, and thus the domain, for the domain of definition, z must not be equal to plus. This is the exception, and for which the denominator is 0, and therefore f of z, the domain of f of z is the domain of definition of f is z not equal to plus or minus I, or all z for which z is not equal to plus or minus I. That is the domain of definition of this. And now for second function f of z, see, we shall consider here itself B solution. F of z is 1 minus mod z square, 1 over 1 minus mod z square is defined for all z except for which this 1 minus mod z square is equal to 0. This is exception, that is, and this means mod z square is equal to 1, or that is mod z is equal to 1, and thus this function is defined except mod z is equal to 1, means mod z must not be equal to 1 in the domain of definition of this function. So therefore the domain of definition of this second function B of this f of z is equal to 1 over 1 minus mod z whole square is mod z not equal to 1, because for mod z is equal to 1 the function is not defined, and it is defined for remaining values of z. So these are the domains of definition of function A and B. Now we shall consider the second problem, which is write the function f of z is equal to z cube plus z plus 1 in this form, u plus I into v. So for solution of second, we have z is equal to x plus iy, z is x plus iy, and therefore f of z is equal to z cube plus z plus 1. In this we shall put the value of z as x plus iy and simplify it. X plus iy cube plus x plus iy and plus 1. So expansion of this cube is x cube plus 3 x square I into y by binomial expansion, or by the formula of a plus b whole cube, and plus 3 x into square of iy, that is I square y square, plus cube of this I cube y cube, and this as it is plus x plus iy plus 1. So we have expanded this. Now see, we know that I square is minus 1 and I cube is minus I. So therefore we shall put these values and we shall collect the real part. This is x cube, the part which does not contain I, and this is minus 3xy square, and here this is minus I, but here x and 1 are real numbers. So this is real part, and what is the imaginary part is plus I we shall take common, and this is 3x square y, and further this is I cube is minus I, since you see I cube is equal to I square into I, and that is minus I, and therefore here it is minus I means minus y cube. I is taken common, and here is I plus y. So thus the real part is this bracket, that is u of x comma y, and this is v of x comma y. So this is u of x comma y plus I v of x comma y. So in this way we can express the given function in the form of u and v. Likewise, we can express in a reverse way. We shall write the third problem to express a function in the form of u and v in terms of z. Or that means a function which is written in this form can be expressed in this form of z. The function which is expressed in the form of x and y is to be expressed in terms of z. That we shall consider as our next problem. See, the third problem is suppose f of z is equal to x square minus y square minus 2y plus I into bracket 2x minus 2xy. So this is the in the form of u of x comma y, and this is v of x comma y, and where z is x plus iy, we have asked to use the expressions. This is actually hint given to solve the problem. We are asked to use the expression x is equal to z plus z bar divided by 2 and y is equal to z minus z bar divided by 2i. These are the values of x and y to be used in this right side, and find the expression of f of z in terms of z. Now see, we have studied this earlier. If z is equal to x plus I into y, then we know its conjugate is x minus I into I, and if you add it this, the addition is z plus z bar is 2x, and therefore x is z plus z bar divided by 2, and if you subtract this, then this gives z minus z bar, x cancels and it is 2iy, and therefore y is z minus z bar divided by 2i. So it is simple to verify these values, and simply we have to put x and y on the right side and simplify this. Solution for this is f of z. F of z is x square minus y square minus 2y plus I times 2x minus 2xy, and therefore this is x square, x is z plus z bar divided by 2 square, minus y is z minus z bar divided by 2i whole square, minus 2 into y, again it is z minus z bar divided by 2i, and plus I into bracket. Now, so I shall write this in bracket as x is z plus z bar divided by 2, and minus 2x, see it is 2 times x, so this 2 gets cancelled, and simply we should write z plus z bar, z plus z bar for 2x. 2x is z plus z bar, and similarly here 2x is z plus z bar, but y is z plus z bar, z minus z bar, z minus z bar divided by 2i. So this is the expression of the given function in terms of z and z bar, and now that is to be simplified. This is equal to f of z is, see the square, after squaring the denominator square is 4, and yes, we can write 1 by 4 common, and in bracket the expansion I shall write in bracket z square plus 2z z bar and plus z bar square. Similarly here, but you see it is 4I square, 1 upon 4I square, and I square is minus 1, so that minus 1 and this minus becomes plus, so it is plus 1 by 4. And into bracket again the expansion of z minus z bar, z square minus 2z z bar plus z bar square. And here we can cancel 2 here, and it is 1 upon I. But 1 upon I we shall multiply it by I, and that will be minus. And if you multiply the denominator and numerator by I, actually we are rationalizing the denominator, and then it becomes I square at denominator. I square is minus 1. So that minus 1 and this minus becomes plus, and we have to multiply the numerator by I. So I shall write directly it is Zi minus Z bar I. Multiplying here by I, you note this. And further, so this is Zi, we shall multiply by I inside the bracket, and that is plus Zi plus Z bar I. And next is here we see this I and this I cancels, and what remains is Z plus Z bar, Z minus Z bar, and it is Z square minus Z bar square, and this minus sign is there, minus Z square minus Z bar square. You note this, it is the used here, the formula is used as a plus b into a minus b, a square minus b square. And now further this is equal to, you see this term cancels because it is the same term with positive and negative sign. And now 1 by 4 z square plus 1 by 4 z square, that is it is 1/2 z square. Similarly, 1 by 4 z bar square and 1 by 4 z bar square, it is half z square plus half z bar square. And here you see zi cancels, not this but this z bar I cancels. Z bar I and plus Z bar I cancels, and Zi plus Zi is twice Zi, and here it is minus Z square plus Z bar square. So further you see this will be half Z square minus Z square, so that is minus half Z bar square. And you see, and plus Z bar square, and this is half Z bar square. So some calculation we have to check here. So here is a minus sign, so we have made I have made a mistake here, so this is minus. And now you see this cancels, not this one, the square term will cancel. This is 1 by 4 z square, this cancels, and z bar square also cancels, so this z square, z bar square will cancel, and what remains is 2 by 4 and plus 2 by 4, that is 4 by 4, which is z bar. Z bar will remain, and here this is 2zi plus 2zi will remain minus z square plus z bar square. So this will remain, but I think there is something wrong, because you see this is this is the expansion we have written, minus 2, and here 2 cancels and it becomes plus zi minus z bar I, that is right, and then this is 2x, and this is 2x z plus z bar. So z plus z bar, I into z plus z bar, and minus this is half, it is half, I cancels but it is half, so this is half, minus half. Note this, I have forgotten this half, and now this is minus half z square and plus half z bar square. So this will be, so I am sorry, I have made a mistake in simplifying this expression, and we shall correct it. See the square of this, so I shall write 1 by 4 common, and in bracket it is z square plus 2z z bar and plus z bar square, and this you should see, we multiply the numerator and denominator by I outside but that is not necessary here, because the square is 4I square and I square is minus 1. So that minus 1 and this minus 1 becomes plus. So it is plus 1 by 4, and into bracket it is expansion of z minus z bar, z square minus 2z z bar and plus z bar square. And here we should multiply the numerator and denominator by I. 2 cancels and this becomes I square at denominator, and that becomes plus, and at numerator we should have to multiply by I. So this is zi minus z bar I, and now this is plus zi plus z bar I, and now you see the last is, this is minus, here we shall multiply the numerator and denominator by not necessary, because I cancels with this I, and what remains is half, so minus half, and z plus z bar, z minus z bar, and that is z square minus z bar square, and this is now you see which term cancels is this one, and 1 by 4 z square plus 1 by 4 z square, that is 2 by 4, that is half z square, half z square, and similarly plus half z bar square. So these two terms are added, and now this is zi minus z bar I. So this z bar I and this cancels. So zi plus zi is 2zi, and now it is half z square minus half z square plus half z bar square, and again this term cancels, and what remains is half z bar square plus half z bar square is z bar square plus 2zi. So this is the expression of f of z in terms of z. So in this way we can simplify a given function to express it in the form of z. So I hope you will understand this. Thank you for watching the lecture.